So let's get started. What we have done last time, quickly to remind you, we looked at the moments that were coming from the airplane. We first looked at the wing, and then we looked at the wing body, and then we then looked at the tail. Okay, and we haven't really looked at the whole aircraft. That's what I'm going to do now. We are going to add all these moments together and look at the moments at the CG of the airplane. All right. So the last thing we did, we looked at the tail, looked at the moment that was coming from the tail, and the moment after making a lot of simplifications, surely, we obtained this one variable. It's called the horizontal tail volume ratio. I told you it's an important variable in the design of airplanes, that this tail volume ratio is similar for a lot of airplanes. So either you make small wings and a small tail, or a big wing and a big tail, or if you have a small tail, then you need a bigger moment arm. So it's that ratio which is kind of key for aircraft design. Okay? So what we're going to do today is we are going to add everything together. Okay. And we're going to look at the total pitching moment of the aircraft. Total pitching moment of the aircraft. So here what we are going to do basically is we are going to look at Cm. Again, Cm is the non-dimensional pitching moment around the CG of the aircraft, right? Now, don't forget that Cm, Cn, and Cl. Okay, is equal to Cm of the wing body, okay, plus Cm of the tail, all right? And we have calculated this, plus others. And these others are components like the engine. The engine might induce some pitching moment, right? Or anything else that might be on the aircraft that induces a pitching moment. It will be included in this part. Okay. So let's write down what we had found last week. The pitching moment for the wing body was something like this. It was the pitching moment of the aerodynamic center of the wing body plus CL times H minus HN wing body, okay, minus VH times CLT, that is the tail, plus others. And that was a minus, if you recall. We had this minus over here, okay, and we had that for the wing body, you see. And we said this is the wing body. We actually looked at the wing, and we added the body over here. So it's the wing, it's the moment around the aerodynamic center, the angle of attack of the wing, and so on and so forth. So it's all here. Okay? So this is what it looks like. This part here belongs to the wing body, and this part here belongs to the tail. All right. So what I want to do here is now we would like to calculate Cm alpha from this, okay? Because we have found that Cm alpha has to look like that, right? It has to be negative Cm alpha, Cm versus alpha. We have looked at this in the previous lectures. So Cm alpha must be negative, right? So let's see what makes this equation negative, all right? So we are simply looking at del Cm del alpha, okay? So we are going to take the derivative over here with respect to alpha of each of these terms. So, and that will look like this. Let me do it here on this side, so I have more space. Del Cm aerodynamic center of the wing body, del alpha, so that's the first term, plus del Cl del alpha h minus h n wb, which is really the non-dimensional distance, right, between the aerodynamic center and the center of gravity, minus Vh, that's a constant, right, times del Clt by del alpha plus others. Of course, if there's something else, it will be in others. Okay? So here we have it. Okay. Let's start with the first one. Let me get a colored pens here. Okay, let's start with the first one. We are looking at the change of the pitching moment at the aerodynamic center of the wing body with respect to alpha. What would that be? 0. Why is that? Because the pitching moment does not change with respect to alpha at the aerodynamic center. That's the definition of the aerodynamic center. I think last week the question was, which point are we using to take the moments, right? Because at the end there are the pressures around the airfoil or the wing, and we are choosing one point and taking the moment with respect to that point and move all the forces moments over there. We can move it anywhere, right? We can move it to the CG and so on and so forth. But when we move it to the aerodynamic center, the nice thing about the aerodynamic center is that it will not change with angle of attack. So and here you see the benefit right here. Okay? If this was not at the aerodynamic center, then this term would still exist here. So this goes to 0 because, yeah, as I said, the aerodynamic center is, let me use the green one, because that's equal to 0. Okay. All right. This is del Cl alpha. Okay, del Cl alpha. This is basically the lift curve slope, right? Del Cl alpha is basically the lift curve slope. So that's del Cl alpha of the airplane, of the wing body. Okay, this is of the wing body. You have a similar term over here, which is Cl alpha, basically the lift curve slope of the tail. Okay, so how does the tail change that? All right. So that's that. Okay, so let's continue then. We have Cm alpha is equal to Cl alpha H minus Hn Wb minus Vh times Cl alpha T. Okay, so if you look at this equation now, a few things. First of all, this one here has something to do with the geometry, right? This is the geometry. Like what your wing body looks like in terms of Cl versus alpha, right? So it has something to do with the shape of your airplane. Okay, this one here is the same. It has something to do with the shape of your wing or your horizontal tail, right? Cl alpha. So if you choose a different airfoil, this will change. So it's the shape. And since this belongs to the wing body, it is the fuselage plus the wing, how you choose the geometry. Okay, this one here is again geometry. This is part of your design. Geometry. I call this geometry, I mean, what I mean is a shape. Okay, so this is again geometry. How big is your wing? How big is the distance to the tail, and so on and so forth. Now this one here, this was the distance. Remember that? This is the distance here of the aerodynamic center of the wing body, right? H and C bar. It's a function of C bar, non-dimensionalized, but it is a distance to the aerodynamic center. Okay? So this one here is simply the geometry again, because if I change the shape of the aircraft, then the location of the aerodynamic center will change. So that will be this one here. Okay? So we have one thing left here, this one here, and that's the location of the center of gravity. Okay? That's the location of the center of gravity. So now that one is not really the geometry. This is the distribution of mass. How you distribute the mass. So after you design this thing, it looks like you can check this H and find the location where Cm alpha will change. So we have established previously, if Cm alpha is less than 0, then the aircraft will be statically stable. If Cm alpha is greater than 0, it will be statically unstable. Okay? And you can see from this equation that you could actually move the location of the CG such that you can make this aircraft, the Cm alpha, positive or negative, because VH is a positive number. CL alpha, I hope it's a positive number. I mean, if you design it nicely, right? CL alpha must also be a positive number, hopefully. So since you cannot really play with the aerodynamic center, maybe we can play with the center of gravity location to see when we become stable or unstable, you see? So you see that if Cm alpha is equal to 0, that's a critical one, right? Where is the location of the CG such that if I move the CG over here, we are right at the boundary, which means a little bit to the left or a little bit to the right will make it stable or unstable. Okay? So that's what we are after here. Where should be the location of the CG, which is basically the H. Where should be H? Such that Cm alpha is equal to 0. So the reason I'm looking for Cm alpha is equal to 0, as I said, it's the boundary. A little bit to the left of that point, it will make it stable. A little bit on the left or right, it will make it stable or unstable. So this is kind of the critical point. So that's what we like to find now. Okay? So that's a goal. So the way I'm going to find this is actually not very difficult, but the result will be very significant. It will be a very fundamental result. So I'm going to take this equation, set it equal to 0, and then find H. I mean, that's what I'm going to do. So Cm alpha, we are looking for the point where it is equal to 0. So the equation will be simply 0 is equal to, right, CL alpha, H minus Hn wing body, the aerodynamic center of the wing body, minus VH times CL alpha T plus others. So I'm going to get h from this equation. H will be equal to, let me put it here. So h will be equal to hn of the wing body minus 1 over CL alpha minus VH bar CL alpha of the tail plus others. Okay? So this is the point. This is the point where the CG is for alpha equals 0. So if the CG is here, CG is at h, then Cm alpha is equal to 0 for this aircraft, and it will be right at the boundary. Okay. Now let's look at it from another point of view. If Cm alpha is equal to 0, first of all, any questions up to this point? Do you understand what I'm doing? I mean, it's not very difficult, but you have to understand it. Is there any questions? Okay. So let's look at it from another point of view. If Cm alpha is equal to 0 for the whole airplane, now we're talking about the whole airplane, right? If Cm alpha is equal to 0, and still m is the moment around the CG of the airplane. It is still the body fixed coordinate system, CG, moment around the CG in the body y-axis and everything, still consistent with everything we have done so far. If Cm alpha is equal to 0 at the CG, right? What does it mean? What is Cm alpha is equal to 0, which means there's no change in the pitching moment with respect to alpha. What kind of a point would that be? It is the aerodynamic center, right? This is kind of the definition of the aerodynamic center. We said if the angle of attack does not change with, if the moment does not change with angle of attack, we call that point the aerodynamic center of a wing or of an airfoil. And here, the moment here is about the CG, of course. But if I move the CG to a certain point right here, Cm alpha does not change anymore. Alpha does not change with respect to, moment does not change with respect to alpha. So therefore, this point, this special point where you put the CG, we call it the neutral point of the aircraft. Put a little n over here. It's the neutral point of the aircraft. And put an n over here as well. This is the definition of the neutral point of the aircraft. It is a point. Now, the definition has changed a little bit because now we have a center of gravity. You know, in the airfoils or in the wings, we really don't talk much about the angle of the center of gravity. We just say, it's the point of the aerodynamic point. If you take the moment with respect to that point and you change the alpha, the moment will not change. That's the point, and it is purely because of the geometry of that wing, right? But here, now we have the concept of center of gravity. And the definition of the aerodynamic center of an airplane has changed a little bit because we are defining the moments with respect to the center of gravity, okay? So the definition has changed a little bit. The definition now says, if you move the CG to a certain point on the airplane, and you find a point, a place for that center of gravity where Cm alpha is equal to 0, that point is a special point. We call it the neutral point of the airplane. Okay? So therefore, the definition for the neutral point or the aerodynamic center is the location of the CG of an aircraft for which Cm alpha is equal to 0 is called the neutral point. point of the aircraft. So it's the neutral point. Sometimes it's also referred to the aerodynamic center of the aircraft. Okay? The definition is quite similar, as I said, for the wing and the airfoils. Moment does not change with respect to alpha. But there we didn't really have a concept of the center of gravity. Now we do have it, and the moment is still around the center of gravity. So if you move the CG to a certain point and the moment does not change with respect to alpha, that would be the neutral point of the airplane. And therefore Hn, here, the way I represent it, now from now on represents the neutral point. Okay? Any questions? Is that definition clear? Is that okay? So now we have a definition for the neutral point. What we are going to do next is we are going to remember this equation that we had at the beginning. At the beginning of the class, we wrote the whole moment here, right? And we came all the way to Cm alpha here, right? So what we want to do is we would like to rewrite this equation. Rewrite this equation here. This one. The Cm alpha equation. Not as a function of these variables, the location of Cg, but write it as a function of the neutral point. Okay, we want to rewrite this equation as a function of the neutral point. So this is how we do it. Let's rewrite the Cm alpha equation as a function of Hn. So basically what we are going to do is this. We are going to take this equation here. We're going to take this equation that I just found. Okay? We're going to take this equation. And I'm going to write this part here. Right? This part. Okay? So it will be Hn, right? Minus Hn wing body. Right? There will be a minus times Cl alpha is equal to this part, minus Vh Cl alpha T plus others. So and I'm going to take this part. Okay, so I just rewrote this equation. So I'm just going to take this part and plug it into my Cm alpha equation. Cm alpha is here. This was the Cm alpha that I had at the beginning of the class. H minus HNWB minus VH del Cl tail del alpha plus others. Okay, So I'm going to replace this one with that. So this is the one I had previously, right? So replace this one with that, this, and you obtain a quite fundamental equation now. Almost there, okay? It will be Cm alpha is equal to Cl alpha, H minus Hn wing body, okay? Times that thing, right? Minus or let's say plus H n wing body minus Hn times Cl alpha. So Cm alpha will be equal to then Cl alpha times, these things will cancel, and you will get H minus Hn. And this is our important result. The result is very simple, okay, and I will talk about this equation quite a bit. But you need to understand where it is coming from, okay? We first wrote the moment equations. We found Cm alpha. We set it equal to 0. Find the location of the Cg. Does that mean? Find the location of the Cg where Cm alpha is equal to 0. Call it the neutral point. Okay? And then rewrite this equation as a function of the neutral point and set this into the moment at Cm alpha equation that we have found previously. This is the equation we found previously. We set it in there. And then things will cancel out and so on and so forth, and you get Cm alpha is equal to Cl alpha H minus Hn. Okay? Now, H is the location of the Cg. Remember? It is a location of, it represents the location of the Cg as a distance from the chord line or some reference line. Hn is the location of the neutral point, right? Cl alpha is the Cl alpha of the whole of the wing body, so it's basically the wing body Cl alpha. So it is the lift curve slope, and hopefully it's always positive, right? Okay. So what did we say? Cm alpha must be negative for stability. What does it mean? Cl alpha must be negative. Hn must be bigger than H. Is that right? So if I had something like that, remember that's how we operated. We said this was the chord line, right? That was the chord line, and we said this is here H times C bar, and then this would be Hn C bar, and this is the neutral point, and this is the aerodynamic center. Okay, and this is for a wing, but let's say there's an airplane around it. It doesn't matter, right? We can say there's an airplane around this. That's okay. It's still with respect to this point, or it could be any other reference point. In this case, we took the leading edge of the wing, but it's fine. We can take it anywhere. We could have taken the nose. It doesn't matter. So, what do we say now? Hn must be bigger than H, only then this will be negative. And since this is positive, Cm alpha will be negative if Hn is bigger. Which means, is in this picture Hn bigger? Yes, it is bigger, right? So therefore, this would be a stable airplane according to our logic. I'm sorry, this is not the aerodynamic center. This is the center of gravity. Nobody's saying anything. This is the center of gravity, HC bar, right? Location of the CG. There's no aerodynamic center anymore. Okay, please correct this, CG. So if the neutral point is behind the CG, then this will be a negative number and Cm alpha will be negative, and therefore the airplane will be stable, right? If you move the CG, listen, this is important. If you move the CG onto the neutral point, what's going to happen? CG will be equal to the neutral point. They will be equal. Cm alpha is equal to 0. Well, that's the definition of the neutral point, right? If the CG moves to a certain point where Cm alpha is equal to 0, then it becomes the neutral point. So that's the definition of the neutral point. You move the CG over here, this becomes 0, this is that. If the CG moves towards the back of the neutral point, what happens then? The airplane becomes unstable because this will become larger and this will be positive, and therefore Cm alpha will be positive and the aircraft will be unstable. Okay? And this is a very fundamental result to have stable airplanes in the longitudinal direction. The CG of the aircraft must be in front of the neutral point so that the aircraft is a stable airplane. Okay? Now, you might say, how are you talking about the CG? Why are you moving the CG? I mean, how do you find the neutral point if the CG is in the front of the airplane? The neutral point is really a hypothetical point. Okay? Let's say I have an airplane. And let's say the CG of the airplane is here. Okay? That's it. The CG of the airplane is here. No more questions, no more discussion. Hypothetically, if I move the CG to this point, if I had moved it to this point, and if I had moved it over there, it's just hypothetically, if then Cm alpha would be 0, if I have moved it over here, then this point I would call the neutral point. In reality, I'm not moving the CG. I'm just saying, if I had moved it to this point, then Cm alpha would have been 0. Okay? That point I call the neutral point. But the CG of the aircraft is here. Or vice versa, right? Let's say the CG of the aircraft is here. Let's say this is the CG. Okay, another airplane. CG is here. Question is, where is the neutral point? If I would ask you, where is the neutral point? You said, well, the CG is here. If I had moved the CG here to this point, if I have moved it to the CG, and if the CG was here, then Cm alpha would have been 0 if it was there. So that point I would call neutral point of the airplane. Is the CG here? No, it's here. But if I have moved it over here, it would have been, Cm alpha would have been 0. Okay? Good. Now that we have identified the neutral point of these airplanes, now tell me about stability. Well, if the CG was here, Cm alpha would have been 0. But the CG is over here, therefore Cm alpha will be positive according to this. Because if the CG is behind the neutral point, this will be bigger, this H, and therefore Cm alpha will be positive and the aircraft will become unstable. Same thing over here. Where is the CG? It's here. If I move the CG to this point, Cm alpha will become 0. Okay, then this point I will call the neutral point. Did I identify the neutral point? Yes. Is the CG, the real CG of the airplane, is it in front of the neutral point or behind the neutral point? It is in front. Okay, this airplane is a stable airplane according to our calculations, because Cm alpha will be less than 0 for this, and Cm alpha will be greater than 0 when the CG is over here. Now, of course, remember, this is not the only condition for stability. You also need Cm0 to be positive, right? In zero angle of attack, you want to have a positive moment. But one of the conditions has to be met, and that is if the CG is in front of the airplane and the neutral point is in the back. Any questions so far? Okay. So let's give a short break. I will talk more about this equation, because this equation here and the results we just found in this class is really the cornerstone of longitudinal stability. Have you done, let me just ask you, have you done your summer practice where you built these model airplanes and you throw it with your hand? You built the airfoil, you built the wing, and then you put a little body on that airplane. And what did you do at the very end? You put a weight to the nose, didn't you? That's exactly what you did. You moved the CG to the front. Remove the weight of that airplane. Remove the weight in front of that airplane. What was happening? Did you ever try to throw your airplane without the weight in front of the nose? What happened? Just, or did this? Became unstable. Move the CG to the front. It's magic. You just throw it and it's just like that. Okay? Here's the reason, okay? So every airplane, if you want to have a stable airplane, you have to have the CG in the front and the neutral point in the back. All right? So let's give a break and I'll talk more about this. There's more I want to say about this.